Hello students, welcome to this video. Here in this particular video I am going to explain about the power in wind or wind energy in module number 4, where we are going to discuss how what is the way to calculate power in wind. Okay, so all of you know that power in the wind will possess energy by virtue of its motion. Okay, so any device capable of slowing down the mass of moving air, that means mass flow rate of moving air, like a sail or propeller or blade, which you can extract part of the energy and convert it into useful mechanical energy or useful to work. Okay, so there are three factors which are used to determine the output from wind energy converted. In that, number one is wind speed, number two is a cross section of wind swept by the rotor, and number three is the overall conversion efficiency of the rotor or rotor transmission system and generator pump. Okay, so the major factors that have led to accelerated development of the wind power are as follows. One is availability of high strength fiber composites for constructing large low cost rotor blades, and second one is falling prices of power electronics, and variable speed operation of electrical generators to capture maximum energy. Then next factor, which is very important, improved plant operation pushing the availability up to 95%, and economy of scale as the turbines and plants are getting larger in size, accumulated field experience which will improve the capacity factor, and short energy payback or energy recover a period of about very less time. So all these things are the very important factors which are accelerated in the development of wind energy. Okay, so we know there is no device which is well designed and can extract all the wind wind's energy, because the wind would have be brought to halt, and this would prevent the passage of more air through the rotor. The most that is possible is for the rotor to deaccelerate the whole horizontal column of intercepted air to about 1/3 of its free velocity. Okay, so a 100% efficient aero generator would therefore only be able to convert up to a maximum of around 60% of the available energy, and uh, this wind available energy into mechanical energy. So well designed blades will typically extract 70% of the theoretical maximum, but losses incurred in the gearbox, transmission system and generator or pump. Okay, so including all these losses which could decrease overall wind turbine efficiency up to 35%, and remaining are loss. Okay, so the power developed in the wind can be computed by using concept of kinetics. So I hope all of you know what is kinetics. Correct? No, I know what is all of you know what is kinetics, isn't it? The windmill works on the principle of converting kinetic energy associated with the of the wind or kinetic energy associated with wind to mechanical energy. So we know that power is equal to energy per unit time. Energy per unit time. The energy available is the kinetic energy of wind. The kinetic energy of any particle is equal to 1/2 its mass times the square of its velocity, that is half mv square. Correct, no? So the amount of air passing in unit time through the area A um, with the velocity v is a into v, and its mass m is equal to its volume multiplied by the density rho of density of the air, isn't it? So m is equal to rho into a into v. So where m is the mass of air traversing the area A swept by the rotating plates of a windmill, which may be all type of generator. Okay. So substituting the value of the mass in the expression for the kinetic energy, we obtain K is equal to the kinetic energy K is equal to half into rho A into A into V into V square. Okay, half rho a v into v square, which is equal to half rho a v cube watts. Okay. Okay, so this equation tells us that maximum wind available, the wind available, the actual will be somewhat less because of all the available energy is not possible to extract. Okay, and is proportional to the cube of the wind power always. So it is thus evident that a small increase in wind speed can have a marked effect on the power of the wind. Okay, so because it is directly proportional to cube root of wind energy, wind velocity, isn't it? So the equation tells us that power available is proportional to air density also. 1.2, the density is always 1.225 kg per meter cube at sea level, and it may vary 10 to 15% during the year because of pressure and temperature change. So it changes negligibly with water content. Okay, so the aero turbine with a large swept area has higher power than a smaller area, because power is directly proportional to area also, isn't it? So for diameter d in horizontal axis aero turbines, the area is equal to 5 by 4 d square. So substituting that, you will get available wind is equal to half into rho into 5 by 4 into d square into v cube. So you will get 1 by 8 rho pi d square v cube watts. That is the equation. So I directly arrived that equation. Okay, so this equation, which is available wind power Pw is equal to 1 by 8 rho pi d square v cube watts, tells us that maximum power available from the wind varies according to the square of the diameter of the intercept area, and normally taken to be a swept area of the aero turbine. Okay, so the diameter of the rotor will result in a fourfold increase in available wind power. So the equation gives us insight into why the designer of an aero turbine for wind electric use would place such a great emphasis on turbine diameter. That is very important. So this combined effect of wind speed and rotor diameter variation is very influencing on that equation. Okay, so efficiency of wind turbine, and then power coefficient is you should know about the power coefficient. So power extracted by the rotor is equal to the so we saw power extracted by the rotor is equal to the product of wind speed as it passes through the rotor and the pressure drop. Okay, so this is very important. So in order to maximize the rotor power, it would therefore to be desirable to have both wind speed and pressure drop as large as possible. However, the velocity is increased for a given value of the free wind speed, that is the air density. Okay, so pressure drop increases at first and passes through to a maximum and then decreases. Okay, hence the specified free wind speed, there is a maximum value of rotor speed. So the fraction of the free flow wind power that can be extracted by rotor is called as power coefficient. Okay, so power coefficient is defined as the ratio of power of wind rotor to the power available in the wind, power of wind rotor to the power available in the wind, that is pt means power of the wind rotor at the turbine. Okay, divide to the power available in the wind rotor. So where power available is calculated from the air density, rotor diameter and free wind speed as shown above. Okay, the maximum theoretical power coefficient is equal to 16 by 27 or 0.593. Okay, 0.593. So this value cannot be exceeded by the rotor in a free flow wind stream. So this value is known as Betz limit. Okay, so this is the maximum theoretical power coefficient. Okay, so an ideal rotor, the propeller type blades of proper aerodynamic design would have a power coefficient approaching 0.59, but such a rotor would not be strong enough to withstand a stress to which it is subjected when rotating at a high rate in a high speed where high speed wind stream. Okay, so for the best practical rotors, the power coefficient is about 0.4 to 0.45. Always it should be less than 0.59, and so that the rotors cannot use more than 40 to 45% of the available power. So this in the conversion into electrical power, some of the rotor energy is lost, and overall electric power coefficient of an aerogenerator is in practice is about only 0.35%. Okay, so rotor speed wind velocity interaction, where the force from the above equations in actuality it is not constant. The velocity v is not constant, but it is represented by a statistically noisy wind speed time curve, that is Vt. So the force F that can be calculated by using equation F is equal to half rho A at into V square, where then we can able to calculate the torque is equal to 1 by 2 into or F into R. So if F the value of F is equal to half rho A T V square, so substituting that we will get half into rho A into AT into V square into R. Okay, so then where R is the radius of the rotor, so it is the maximum theoretical torque. So in practice the rotor shaft can develop only a fraction of this maximum value, so we can able to get this value Ct is equal to 2T into that is torque of turbine into rho A V square into R, where Ct is the torque coefficient and Tt is the actual torque developed by the rotor. Okay, so the equation tells us that for a non-steady state wind, it is necessary to cube the measured wind speed and then take the average to wind power available. So it is immediately obvious that this non-steady state case is more complex than simple steady state. Okay, so we can calculate the maximum power by using this equation. Okay, so we can calculate maximum power by using the above equation. So consider the horizontal axis propeller type windmill and which is most common type of used today. So assume that the wheel of such a turbine has thickness AB and let Pi and Vi are the wind pressure at inlet and pressure and velocity at upstream of the turbine, that is at inlet, and Pe and V are pressure and velocity at downstream the turbine at outlet. So V is always less than Vi because kinetic energy is extracted by the turbine. So considering the incoming air between I and A as a thermodynamic system and assuming that air density remains constant throughout, so by applying Bernoulli's equation, we can able to write PIV into Vi square by 2Gc plus PAV into Va square by 2Gc. This is the general form of equation for steady state. So Z1 plus V1 square by 2G plus U into P1 V1 into del Q is equal to Z2 into V2 square by 2G plus U2 plus P2 V2 into delta WSF. This is actually general form of Bernoulli's equation, where Z1 is the potential energy, V1 square by V square by 2G is kinetic energy, U is internal energy, rho V is flow energy, delta Q is net heat added, and delta WSF is net steady mechanical work done. So that is all remains 0. So only the thing is remaining is Pi into rho Vi square by 2Gc plus Pa into rho Va square by 2Gc, where V and rho are the specific volume and its reciprocal is density. Okay, so the exit this is for inlet region. Similarly, we can write for exit region also. So if you minus inlet minus exit PM minus PB, then you will come across with one form. Okay, which is called as speed ratio or a tip speed ratio. Okay, gamma is equal to R omega by V, which is equal to 2 pi n R by V. So where this angular velocity and n is the rotational speed of the rotor, and gamma is the optimum tip speed ratio. So we know that power coefficient Cp is equal to 2 pt by rho A T V cube. So substituting that, we will get we know that Cp by Ct is equal to gamma. So substituting that, we will get, and also we know that maximum limit is 0.59. So substituting that, maximum power Pt max is equal to half into rho A ATV cube by 16 to 27. Okay, this is the equation, or 0.593 into half rho AV cube. Okay, this is the maximum power for wind speed.